Hello, my lovely dreamers, and welcome back to Hayfy Sleep. Whether you're curled up in bed as the moon shines brightly or you're taking a quiet moment for yourself in the middle of a busy day, I'm so glad you found your way here. Before we drift into today's incredible journey, if you're new to this cozy corner of the internet, consider subscribing to the channel. And if you're already part of our family, welcome back. If this video helps you relax or learn something new, giving it a like is a wonderful way to let me know. Now I have a question for you. I love imagining all of you, listening from all over the world. So if you feel like it, please take a second to comment down below and tell me where you are and what time it is for you right now. Are you watching from a bustling city at noon or a quiet village at midnight? It's always so magical to see our community connected from every corner of the globe. Now get comfortable, close your eyes, and let your mind wander. Tonight, we're going on a journey to the very edge of cold, to a place where the normal rules of physics fade away and the quantum world takes over. We're exploring one of the most fascinating mysteries of our universe. What happens to atoms at absolute zero? It's a story of perpetual motion, quantum rebellion, and a chill so profound it reveals the secret, shimmering nature of reality itself. So let your thoughts settle. Take a deep breath in, and let's begin. Imagine, if you will, the coldest moment you've ever experienced. Perhaps it was a winter morning when the air felt so crisp it seemed to crackle with each breath. Or maybe it was that first shocking plunge into an icy body of water where the cold steals your breath and makes your heart pound in your chest. Now, take that feeling, that sensation of intense cold, and multiply it beyond anything you've ever known. Beyond the frozen tundras of the Arctic, beyond the dark shadows of deep space, beyond what most of us can even comprehend. What you're approaching is a fundamental limit of our universe, a temperature so extreme that it redefines our understanding of cold itself. This is the story of absolute zero, the ultimate cold, a temperature that has captivated scientists for centuries and continues to reveal the strange and wonderful secrets of our physical world. When we talk about temperature in our everyday lives, we're usually discussing something quite practical. Whether we need a jacket outside, if our oven is hot enough to bake bread, or why ice cubes clink in our glass of lemonade on a summer afternoon. These experiences are so familiar that we rarely stop to consider what temperature actually is, at its most fundamental level. Think of a crowded room where people are constantly moving, bumping into each other, changing direction, some moving quickly and others more slowly. Now imagine that instead of people, these are atoms and molecules, the building blocks of everything around us, including the air we breathe, the water we drink, and even our own bodies. Temperature, you see, is simply a measure of how vigorously these tiny particles are moving and vibrating. When something is hot, its atoms and molecules are dancing with tremendous energy. When something is cold, they're moving much more slowly, perhaps swaying gently rather than dancing wildly. But what happens if we take this slowing down to its ultimate conclusion? What if we could remove every last bit of this vibrational and motion energy from a substance? This question leads us to one of the most fascinating concepts in all of physics, absolute zero, the temperature at which particles contain the minimum possible thermal energy, a chilling 273.15 degrees Celsius, or 459.67 degrees Fahrenheit. At this theoretical limit, something extraordinary happens, or rather, stops happening. The frantic dance of atoms slows to what we might imagine as their most minimal quantum mechanical sway, retaining only what physicists call zero-point energy, the irreducible minimum motion required by the very laws of quantum physics themselves. The pursuit of absolute zero isn't merely an academic exercise. It's a journey that has transformed our understanding of the physical world and led to remarkable technological innovations that shape our modern lives. From the MRI machines that allow doctors to peer inside our bodies without surgery to the sophisticated sensors that enable GPS systems to guide us to our destinations, the science of extreme cold has become embedded in technologies we now take for granted. But beyond these practical applications, the story of absolute zero is one of human curiosity and persistence, of scientists across generations pushing the boundaries of what seems possible, and in doing so, discovering entirely new states of matter and rewriting the textbooks of physics. As we embark on this journey together, I invite you to set aside your preconceptions about temperature and cold. Prepare to enter a world where fluids flow uphill, where electrical currents flow forever without resistance, and where matter behaves both as particles and as waves. This is the strange and counterintuitive realm of ultra-low temperature physics, a world that exists at the very boundaries of what nature allows, a world that begins at absolute zero. The story of absolute zero begins not in modern laboratories with their sophisticated cooling systems, but in the minds of curious thinkers centuries ago, who observed the world around them and asked simple yet profound questions about the nature of heat and cold. Long before we had precise instruments to measure temperature, before we understood the atomic nature of matter, natural philosophers recognized that heat flows from hotter objects to colder ones, and they wondered, is there a limit to how cold something can become? One of the earliest recorded considerations of an ultimate cold comes from the Greek philosopher Parmenides in 450 BC, who conceived of what he called frigidum primum, a hypothetical substance that was as cold as possible and could impart coldness to other objects. This concept of a fundamental cold substance persisted through the ages, with various naturalists proposing different candidates for what this ultimate cold might be. Some believed it resided within Earth, considered one of the four classical elements, others within water, air, or even nitre. What they shared was the intuition that there existed some body or other that is of its own nature supremely cold, and by participation of which all other bodies obtain that quality, as Robert Boyle would later articulate in his 1665 work, New Experiments and Observations Touching Cold. The scientific journey toward quantifying absolute zero took a significant leap forward in the early 18th century with French physicist Guillaume Amantin. Now, Amantin was a fascinating character, made all the more remarkable by the fact that he was severely hearing impaired, which some historians suggest led him to be a more meticulous observer, less distracted by the noise of the world and more focused on the quiet details of experimental data. In 1703, he turned his keen mind to the problem of temperature measurement, but he decided to take a completely different path. Instead of using a liquid sealed in a glass tube, which could be influenced by so many factors, he built a better air thermometer. An air thermometer is a simple but clever device. Think of a U-shaped glass tube where one end is sealed and contains a small quantity of dry air trapped by a column of mercury in the tube. The open end of the tube is exposed to the atmosphere. Now, the fundamental idea is this. When you heat the sealed end with the air, that air expands, pushing the mercury column down on its side and up on the open side. When you cool it, the air contracts and the mercury moves the other way. The difference in the height of the mercury between the two sides of the tube gives you a measure of the pressure of the trapped air. Amintins, with painstaking care, began to heat and cool his apparatus, taking measurements and noting something extraordinary. He saw that as the temperature dropped, the pressure of the air, what he poetically called the spring of the air, also dropped in a beautifully predictable, linear fashion. It wasn't chaotic, it was like a clockwork mechanism. The colder it got, the less spring, the less push the air seemed to have. This is where Amintins made a conceptual leap that was decades, if not a century, ahead of its time. He followed this line of reasoning. If cooling the air reduces its pressure in a straight line, what happens if I keep cooling it? He mentally extended his graph, this straight line of descending temperature and descending pressure, further and further down. He reasoned that there must be a point, a specific temperature, where the spring of the air would be completely gone. The air would have no pressure left. Its particles would have collapsed into a state of complete rest, offering no resistance, no push, nothing. This, he proposed, was the ultimate cold, the absolute zero of temperature. On the scale he was using, his calculations placed this point at about 240 degrees on our modern Celsius scale. Now just sit with that for a moment. The value we accept today with all our advanced technology and quantum mechanics is 273.15 degrees Celsius. In 1703, with a glass tube, some air, and some mercury. Amundsen's got within 33 degrees of the correct answer. It was an astonishingly good estimate. But what's even more insightful and what truly marks his genius is that he didn't think of this as a temperature you could actually achieve, like the freezing point of water where you can just make ice. He understood it as a theoretical boundary, a limit imposed by nature itself. He realized that you could get closer and closer to it, but actually arriving there might be impossible. This idea of an unattainable ultimate cold was a profound philosophical and scientific insight that would echo through the ages. After Amundsen's, the scientific baton was passed, and throughout the 18th century, other great minds tried to refine this number. It was a bit like trying to triangulate the position of a distant star with increasingly better telescopes. For instance, in 1779, a polymath named Johann Heinrich Lambert, who was busy making contributions to everything from mathematics to map-making, looked at the data and suggested that 270 degrees Celsius was probably a better estimate for this absolute cold. He was even closer, just 3 degrees off the modern value. But not everyone was on the right track. Meanwhile, scientific giants like Pierre-Simon Laplace and Antoine Lavoisier, who were brilliant in their own right. Lavoisier is famously the father of modern chemistry, proposed values that were wildly off, like 1,500 or even 3,000 degrees below the freezing point of water. This tells us something important about the process of science. It's not a straight guaranteed march to truth. It's a messy, zigzagging path filled with wrong turns and brilliant mistakes. The uncertainty was immense because they were still grappling with the fundamental nature of heat itself. Was it a fluid, called caloric, that flowed from hot objects to cold ones? The tools and the theoretical frameworks were still in their infancy. Then, between 1787 and 1802, the pieces of the puzzle began to snap into place with a satisfying clarity. This period saw the work of 3 scientists, Jacques Charles, John Dalton, and Joseph-Louis Gay-Lussac, who all independently discovered and refined a crucial piece of the puzzle, a relationship we now call Charles's Law, though sometimes, in a nod to the often unfair nature of scientific fame, it's called Gay-Lussac's Law. What did they discover? They found that if you keep the pressure of a gas constant, the volume of the gas and its temperature are in a direct linear relationship. It's a beautifully simple idea. Imagine a syringe with its plunger pulled out, filled with air. If you seal the tip so no air can escape, you have a fixed amount of gas. Now, if you heat the syringe, what happens? The plunger gets pushed out, the volume increases. If you cool it, the plunger gets pulled in, the volume decreases. Charles Dalton and Gay-Lussac did this with meticulous precision and found that for every single degree Celsius you drop the temperature, the volume of the gas decreased by a very specific constant fraction, 1/273 of its volume at 0 degrees C. Let's make this real with a simple thought experiment. Imagine you have a balloon filled with a theoretical ideal gas at 0 degrees C, and its volume is exactly 273 liters, a big balloon. If you cool it down by 1 degree Celsius to 1 degree Celsius, its volume would shrink by 1/273 of its original size, so it would now be 272 liters. Cool it down to 2 degrees, and it becomes 271 liters. You can see the pattern. Now let's follow this pattern all the way down. If you cool it to 100 degrees C, the volume would be 173 liters. At 200 degrees C, it would be 73 liters. The volume is dropping in a perfectly straight line. Now, the inevitable, inescapable mathematical conclusion: if you could somehow cool this gas to 273.15 degrees C, the volume would be 273.15, which is essentially 0 liters. The gas would, in theory, occupy no space at all. Of course, we know now that in the real world, gases turn into liquids and then solids long before this point, and quantum mechanics tells us matter can't truly vanish. But for this idealized perfect gas, the extrapolation was clear and compelling. The number 273.15 wasn't arbitrary. It wasn't based on water or human body temperature. It emerged naturally from the fundamental behavior of gases themselves. It was a number written into the very laws of physics. This set the stage perfectly for the final act in this particular chapter of our story, the entrance of William Thomson, who would later be crowned Lord Kelvin for his scientific achievements. By 1848, the world of physics was buzzing with new ideas about energy, work, and heat. The new science of thermodynamics was being born through the work of people like James Prescott Joule, who showed the mechanical equivalent of heat, and Sadi Carnot, who thought deeply about the efficiency of heat engines. Kelvin, a brilliant synthesizer and thinker, stood on the shoulders of these giants and of Amintons, Charles, and Gay-Lussac. He saw the profound significance of that number, 273.15 degree rings. He realized that this wasn't just a convenient point on the Celsius scale. It represented a fundamental, universal baseline. It was the true 0 point of temperature. So, he proposed a new scale, one that was independent of the properties of water or any other substance. He declared that this natural zero should be called zero. Zero on what we now call the Kelvin scale. On this scale, you don't use degrees, you just say kelvins. So 0 Kelvin is absolute zero. And because the size of a Kelvin unit is the same as a Celsius degree, water freezes at about 273.15 K and boils at about 373.15 K. This was a revolutionary shift in thinking. The Kelvin scale wasn't just another way to measure temperature, it was a statement about the nature of reality. It said that temperature has a true absolute minimum. You can't have less than 0 joules of thermal energy. In the same way, you can't have less than $0 in your bank account without going into debt, but with temperature, debt isn't an option. This 0 point is a fundamental boundary of our universe, as bedrock as the speed of light. Kelvin's insight transformed temperature from a relative, somewhat arbitrary measurement into an absolute quantity, paving the way for the precise mathematical formulations of thermodynamics that would power the industrial and scientific revolutions to come. It was the final, elegant capstone on a century and a half of brilliant deduction, from Amintons' first glimpse of a missing spring to Kelvin's declaration of an absolute zero. But the story doesn't end with Kelvin. The establishment of absolute zero as a theoretical concept opened up new questions. What actually happens to matter as it approaches this temperature? Can we ever actually reach it? What strange phenomena might occur in this extreme regime? These questions would drive experimental physics forward into the 20th and 21st centuries, leading to discoveries that would challenge our very understanding of the physical world. To truly appreciate the significance of absolute zero, we need to understand how we measure temperature and why the Kelvin scale is so fundamentally different from the Celsius and Fahrenheit scales we use in our daily lives. So let's start with what we know with the thermometers on our walls and the ovens in our kitchens. We're all familiar with the Celsius scale. It feels natural, doesn't it? 0 is where water freezes, 100 is where it boils. It was designed by Anders Celsius to be incredibly practical, a perfect tool for everyday life on Earth. When the weather report says it's 0 degrees C outside, we know to watch for ice on the roads. When a recipe says to bake at 180 degrees, we know exactly how to set our oven. But here's the thing we rarely stop to consider, that 0 is completely arbitrary. It's a convention, a human-made agreement. We decided that the particular point where liquid water turns to solid ice under one specific atmospheric pressure would be our 0. But there is still a tremendous amount of heat, of jiggling atomic energy, at 0 degrees C. The water molecules in ice are still vibrating wildly. They're just locked in a crystalline structure. If we were aliens from a planet where the primary liquid was ammonia, we might have set our 0 at the freezing point of ammonia. If we were beings of pure energy, we might have a completely different reference point. The Celsius scale is brilliant, but it's provincial. It's a map of temperature that's centered on a very Earth-like, water-based experience. Then we have the Fahrenheit scale, which feels even more peculiar when you look at its origins. Daniel Gabriel Fahrenheit, a talented instrument maker, was trying to create reproducible thermometers. For his 0, he used the temperature of a freezing brine solution, a mixture of ice, water, and ammonium chloride. This was the coldest temperature he could reliably reproduce in his lab. It was a stable point, a good benchmark for a craftsman. For the top end of his scale, he initially used the human body temperature, which he pegged at 96 degrees. Why 96? It's thought because it's a number easily divisible by 2, 3, and 4, making it easy to mark the graduations on a glass tube by hand. So, the Fahrenheit scale, which millions of people use every day, is fundamentally based on the freezing point of a specific salty slush and the temperature of a human armpit in early 18th century Germany. It works, it's consistent, but my goodness, it's a relative scale built on some very human-centric, almost quirky foundations. There's nothing in the fundamental laws of the universe that points to a brine solution as a cosmic zero point. This is where the stage was set for a revolution, for a scale that wasn't about us, but about the universe itself. And this is where Lord Kelvin enters our story. He looked at all this, the water freezing, the brine slushing, the body temperature measuring, and he saw a deeper pattern. Scientists like Jacques Charles and Joseph Louis Gay-Lussac had already shown that if you take a gas and cool it down, its volume shrinks in a perfectly straight, predictable line. If you cool it by 10 degrees, its volume decreases by a certain amount. Cool it by 20 degrees, it decreases by twice that amount. It's a beautifully linear relationship. Now, Kelvin asked a simple but profound what-if question. He took this straight line and extended it in his mind, far beyond where any real gas could actually exist as a gas, down, down, down into the realm of the deeply theoretical. He followed that line all the way to the point where the volume of this theoretical, perfect, ideal gas would hit zero. That point, that temperature, he realized, wasn't just another number on a man-made scale. It was a natural stopping point. It was the temperature where the particles of that gas would have no thermal energy left to give up. They would, in theory, stop moving entirely. He called this temperature absolute zero. And so he created a new scale, the Kelvin scale, and he declared that this absolute zero would be its foundation. 0 Kelvin. Not 0 degrees Kelvin, just Kelvin. The degree is dropped because it's not a relative measurement anymore. It's an absolute quantity, like a number of apples or a distance in meters. On this scale, water freezes at about 273.15 Kelvin and boils at about 373.15 Kelvin. Notice that the difference between freezing and boiling is still 100 units, just like Celsius. A 1 degree change in Celsius is exactly the same as a 1 Kelvin change. The scales are cousins. They just start in different places. One starts at a convenient human landmark, water freezing. The other at a fundamental universal boundary, the end of thermal motion. Now, for completeness, we should mention that there is an absolute version of the Fahrenheit scale too, called the Rankine scale. It takes the Fahrenheit degree size, the tiny, finely grained units that Americans are used to, and sets its zero at absolute zero. So 0 degree R for Rankine is the same as 0K, which is the same as 459.67 degree. It's not very common, but it exists mostly in some specialized engineering fields in the United States, a testament to the stubborn persistence of the Fahrenheit system. The conversions are mathematically simple. To go from Celsius to Kelvin, you just add 273.15. To go from Fahrenheit to Rankine, you add 459.67. But why does this all matter, you might ask? It sounds like a philosophical difference. Why can't physicists just stick with Celsius and be done with it? This is where we get to the heart of the matter, and it's crucially important. This distinction is the difference between a map that's useful for finding a local coffee shop and a map you'd use to navigate the ocean. When you're dealing with the fundamental laws of the universe, the deep mathematics that describe how energy flows and how matter behaves, the relative scales break down. They simply don't work in the equations. Let's take one of the most famous equations in physics, the ideal gas law. PV is equal to nRT. In that equation, T is temperature. If you plug in a temperature in Celsius, say 0 degrees C for T, the equation gives you nonsense answers. It fails. It only gives you physically meaningful, predictive results if you use Kelvin. Why? Because the law relies on ratios. It depends on the proportionality between temperature and other properties. And ratios only make true physical sense when your zero is a real, absolute zero. Think of it like this. If I have a bank account with $10 in it, and you have one with $20, I can say you have twice as much money as I do. That makes sense because $0 means the absence of money. But if I invent a new banking system where zero is actually defined as having $100 in your account, let's call it relative dollars or R dollars, then my $10 would actually be $110 real dollars, and your $20 would be $120 real dollars. You don't have twice as much money as I do in reality. The ratio is broken because the 0 point is fake. This is exactly what happens with temperature. If I say a star at 20 degrees C is twice as hot as a star at 10 degrees C, I'm speaking nonsense because 0 degrees C isn't the absence of heat. In reality, that 10 degrees C star is actually 283.15 K, and the 20 degrees C star is 293.15 K. The second star is not twice as hot, it's only about 1.035 times as hot. The Kelvin scale allows us to make true, meaningful comparisons. It allows us to calculate the theoretical maximum efficiency of a heat engine, like a car engine or a power plant, which depends on the ratio between the temperature of the hot source and the cold sink. These ratios are the bedrock of thermodynamics, and they only function with an absolute scale. Now, it's vital to understand that this value, 273.15 degrees C, 0K, isn't just a number we found by cooling a gas and watching it disappear. In the real world, long before a gas gets anywhere near that cold, it condenses into a liquid and then freezes into a solid. The idea of a gas's volume hitting zero is a theoretical extrapolation from the behavior of what we call an ideal gas. A simplified, perfect model of a gas where particles are point-like and don't interact with each other. It's a mathematical limit, much like the concept of a perfectly frictionless surface. We never see it in reality, but it's an incredibly powerful concept that reveals a fundamental truth. The fact that this same number, 273.15 degrees C, pops out from completely different lines of inquiry, from the efficiency of heat engines, from the statistical distribution of energy in a system, and later from the equations of quantum mechanics, tells us that we haven't just found a convenient number. We've discovered a cornerstone of physical reality. Absolute zero is a law of the universe, a boundary written into the fabric of space-time telling energy and matter, you can go no further. It's the universe's ultimate cold shoulder. As we venture closer to absolute zero, matter begins to behave in ways that challenge our everyday expectations and intuition. The familiar rules of physics that govern our macroscopic world seem to transform, revealing a strange and wonderful quantum realm that typically remains hidden at higher temperatures. To understand what happens near absolute zero, we need to follow matter on its journey from the thermal bustle of room temperature down to the quantum quiet of the deep cold. Let's start with a gas at room temperature. The air in the room where you're sitting, for example. The molecules in this gas are moving at astonishing speeds, typically around 500 meters per second, over 1,000 miles per hour, constantly colliding with each other and with the walls of the room. This frenetic motion is what we perceive as temperature. If we could slow these molecules down, we would perceive the air as colder. Now imagine we begin to cool this gas. As we remove thermal energy, the molecules move more slowly, their kinetic energy decreasing. At normal atmospheric pressure, many gases will condense into liquids as we cool them. Oxygen condenses at around 183 degrees C, nitrogen at 196 degrees C. If we continue cooling, these liquids will eventually freeze into solids. But something interesting happens as we approach extremely low temperatures. The classical picture of particles slowing down doesn't tell the whole story. According to quantum mechanics, even at absolute zero, particles don't completely stop moving. They retain what's known as zero-point energy, a minimum quantum mechanical motion required by Heisenberg's uncertainty principle. This principle tells us that we cannot simultaneously know both the exact position and exact momentum of a particle. If particles were to come to a complete stop, we would know both their position, they're not moving, and their momentum, zero, violating this fundamental quantum rule. Therefore, even at absolute zero, particles continue to jiggle with this irreducible minimum motion. This zero-point energy has observable consequences. For example, helium, under normal pressures, remains a liquid even at temperatures arbitrarily close to absolute zero. It doesn't freeze into a solid because the zero-point motion of helium atoms, which are very light and weakly interacting, is sufficient to prevent them from settling into the fixed positions of a crystalline solid. Only under high pressure, which forces the atoms closer together and enhances their interactions, does helium solidify. This is a remarkable demonstration of how quantum effects that are negligible at higher temperatures become dominant players in the ultra-cold regime. As we cool matter further, another extraordinary transformation occurs. The distinction between individual particles begins to blur, and they start to behave as a single collective entity. This phenomenon, known as Bose-Einstein condensation, was predicted by Satyendra Nath Bose and Albert Einstein in the 1920s, but wasn't experimentally observed until 1995, when Eric Cornell, Carl Wieman, and Wolfgang Ketterle created the first Bose-Einstein condensates using ultra-cold atomic gases. In this bizarre state of matter, typically occurring at temperatures just a few billionths of a degree above absolute zero, individual atoms lose their identity and merge into a single quantum wave, behaving more like a single superatom than a collection of individual particles. The journey to these extreme temperatures requires remarkable experimental ingenuity. Scientists use techniques like laser cooling and evaporative cooling to strip atoms of their thermal energy. In laser cooling, carefully tuned lasers are used to bombard atoms from all directions with photons. When atoms absorb these photons, they receive a tiny push. By tuning the laser frequency slightly below the atomic resonance, atoms moving toward the laser light see it as resonant due to the Doppler effect, and are more likely to absorb photons, thus slowing them down. It's like running in the rain. You get wetter in front because you're running into the raindrops. This technique can cool atoms to within a few thousandths of a degree above absolute zero. To reach even lower temperatures, scientists use evaporative cooling, which works similarly to how a hot cup of coffee cools. The most energetic molecules escape as steam, carrying away energy and leaving the remaining coffee cooler. In atomic physics, magnetic fields are used to trap the coldest atoms while allowing the warmer, more energetic atoms to escape, thus cooling the remaining sample. Through these and other techniques, scientists have reached temperatures within a few billionths of a degree of absolute zero, and in some specialized systems even down to a few picokelvin, trillionths of a degree. At these fantastically low temperatures, matter exhibits properties that seem to defy common sense. Superfluidity occurs when liquids, typically helium-4 at around 2 K, lose all viscosity and can flow without friction. A superfluid can creep up the sides of a container and escape, seemingly defying gravity. It can form persistent currents that flow forever without slowing down, since there's no friction to dissipate their energy. If you set a superfluid rotating in a ring, it will continue rotating essentially forever, a dramatic demonstration of the disappearance of viscosity. Similarly, superconductivity emerges in certain materials when cooled below a critical temperature, typically a few kelvins for conventional superconductors. In this state, electrical resistance vanishes completely, and currents can flow indefinitely without any power source. Superconducting magnets, which maintain persistent currents for years, are crucial for technologies like magnetic resonance imaging, MRI machines, and particle accelerators. The Meissner effect, where superconductors expel magnetic fields, allows them to levitate above magnets, a dramatic demonstration of quantum mechanics on a macroscopic scale. These phenomena, Bose-Einstein condensation, superfluidity, and superconductivity, are all manifestations of quantum mechanics becoming visible at macroscopic scales. At higher temperatures, thermal motion masks these quantum effects, but as we approach absolute zero, the random thermal jostling quietens and the underlying quantum nature of matter reveals itself in dramatic and unexpected ways. It's as if we're peeling back the chaotic surface of reality to reveal an ordered quantum world beneath, a world where waves and particles merge, where friction disappears, and where collective behavior triumphs over individual motion. As we delve deeper into the physics of absolute zero, we encounter one of the most fundamental principles governing our universe, the third law of thermodynamics. This law, which emerged from the work of Walter Nernst in the early 20th century, makes a profound statement about the impossibility of reaching absolute zero. While we can approach this ultimate cold arbitrarily closely, the third law tells us that we can never actually arrive there through any finite process. To understand why absolute zero is unattainable, we need to first understand the concept of entropy. Entropy is often described as a measure of disorder or randomness in a system, but a more precise description is that it measures the number of ways a system can be arranged while still looking the same macroscopically. Imagine a deck of cards. A perfectly ordered deck with all cards arranged by suit and rank has low entropy, while a randomly shuffled deck has high entropy because there are many possible arrangements that all look similarly disordered. In thermodynamic terms, entropy also relates to how energy is distributed among the possible states of a system. The third law of thermodynamics states that as the temperature of a perfect crystal approaches absolute zero, its entropy approaches a constant minimum. For a perfect, pure, crystalline substance, this minimum entropy is taken to be zero. Why is this? Because in a perfect crystal at absolute zero, every atom is in its precise proper place in the crystal lattice, vibrating with only the minimal zero-point motion allowed by quantum mechanics. There's only one way to arrange the atoms. They're perfectly ordered. With no disorder and only one possible microscopic arrangement, the entropy is zero. But here's the crucial implication of the third law. If we want to cool something to absolute zero, we need to be able to reduce its entropy to that minimum value. The problem is that all real cooling processes require that we transfer heat from a colder body to a hotter one, which by the second law of thermodynamics can only happen if we do work on the system. As the temperature drops, the efficiency of these cooling processes decreases, meaning we need to do more and more work to remove each additional bit of heat. As we approach absolute zero, the amount of work required to extract the last traces of thermal energy approaches infinity. In practice, this means that reaching absolute zero would require either infinite time, infinite energy, or infinitely complex control over the system. This unattainability principle has been expressed in various ways throughout the history of thermodynamics. Nernst's original formulation, known as the Nernst heat theorem, stated that the entropy change for any isothermal process approaches zero as the temperature approaches absolute zero. A more operational statement is that it's impossible by any procedure, no matter how idealized, to reduce the temperature of a system to zero in a finite number of operations. Think of it like trying to cross a room by always moving half the remaining distance. You'll get increasingly close to the wall, but you'll never actually reach it, no matter how many steps you take. Recent research has further refined our understanding of this fundamental limit. Scientists at TU Wien have investigated how the third law of thermodynamics reconciles with quantum physics. Their findings suggest that in theory, absolute zero might be attainable, but only with infinite resources, specifically infinite energy, infinite time, or infinite complexity. For instance, if we had infinitely precise control over infinitely many quantum particles, we might reach absolute zero in finite time with finite energy. But since such perfect control is impossible in practice, absolute zero remains unreachable. This quantum version of the third law beautifully connects the thermodynamics of cooling with quantum information theory, since cooling a quantum system to absolute zero is equivalent to perfectly erasing all information about its previous states. The behavior of various thermodynamic quantities as we approach absolute zero further illustrates why this temperature is so elusive. The specific heat, the amount of heat required to raise the temperature of a substance by 1 degree, vanishes as temperature approaches zero. This means that as substances get colder, they require less and less heat to change their temperature, which might sound like it would make cooling easier. But the opposite is true. Because specific heat drops to zero, the same amount of heat removal produces smaller and smaller temperature drops as we approach absolute zero. It's like trying to drain the last few centimeters from a swimming pool with a fixed-size bucket. Each bucket removes the same amount of water, but the pool gets shallower more slowly because the same volume represents a greater fraction of the remaining water. Similarly, The coefficient of thermal expansion, how much a material expands when heated, also approaches zero as temperature drops toward absolute zero. This makes intuitive sense. If atoms are already in their minimum energy configuration, heating them doesn't cause them to expand because they're already as compact as quantum mechanics allows. Various other thermodynamic quantities also exhibit this slowing down as we approach absolute zero, making further cooling increasingly difficult. The third law and the unattainability of absolute zero might seem like discouraging limitations, but they actually reveal profound truths about our universe. They tell us that perfect order is an ideal that can be approached but never fully realized, that there's always some residual motion, some quantum fluctuation, some minimal randomness that cannot be eliminated. This isn't a failure of our technology or understanding. It's a fundamental feature of nature, as built into the fabric of reality as the speed of light or the gravitational constant. In our pursuit of absolute zero, we're like sailors chasing the horizon. The journey itself yields remarkable discoveries, even if the destination remains forever out of reach. Each advance toward colder temperatures has revealed new phenomena and new understanding, from superconductivity to Bose-Einstein condensation. The unattainability of absolute zero isn't a barrier to progress. It's an invitation to explore the rich physics that emerges as we approach this fundamental limit. And it's truly remarkable how the quest for cold has moved from a theoretical dream to an engineering reality with world-changing applications. Let's pull back the curtain on the incredible technology that makes this possible and explore the strange new world that opens up just above absolute zero. Imagine trying to photograph a hummingbird's wings in perfect, sharp detail. If the bird is moving erratically, the photo will be nothing but a blur. But if you could somehow convince the hummingbird to stay almost perfectly still, you could capture every magnificent detail. This is exactly what scientists are doing with atoms when they cool them to near absolute zero. At room temperature, atoms are like a swarm of frantic hummingbirds, zipping around at thousands of kilometers per hour, bumping into each other and making it impossible to study their fine details. All that frantic motion is what we experience as heat. The goal of ultra-cold physics is to convince these atoms to slow down, to settle, and to reveal the hidden quantum world that governs their behavior. And to do that, we've had to become master chillers, building some of the most delicate and complex refrigerators in the universe. The workhorses of this deep freeze are devices called dilution refrigerators. If you've ever seen a picture of a quantum computer, it's that chandelier-like structure hanging inside a giant silver can. That chandelier is the heart of the cooling system. These refrigerators work in stages, each one bringing the temperature down a little further, like going down a staircase into a deeper and deeper cold. The initial stages might use conventional refrigeration techniques to get things as warm as a few degrees above absolute zero. Then they use liquid helium to cool further. But the real magic happens at the coldest stage, where a special mixture of two isotopes of helium, helium-3 and helium-4, are used. In a process that seems almost like a thermodynamic sleight of hand, the helium-3 atoms are continuously diluted into the helium-4, and this process itself draws heat away from the system, allowing temperatures to plummet to as low as 10 millikelvin. That's 0.0010 Kelvin, or just 10,000ths of a degree above absolute zero, or even lower, right down to where the quantum chip is housed. It's a delicate, complex, and expensive process, but it's the key to unlocking the power of quantum bits. Another brilliant technique is laser cooling. Think of using the gentle pressure of light itself to slow atoms down. Here's how it works. Atoms absorb light, and when they do, they get a tiny push. Now, because of the Doppler effect, the same thing that makes a siren's pitch sound higher as it approaches you and lower as it moves away, atoms moving toward a laser beam will see the laser's frequency slightly shifted. Scientists can tune a laser so that its light is exactly the right frequency to be absorbed only by atoms moving toward it. When an atom absorbs that photon of light, it gets a kick backward, slowing it down just a little. By surrounding a cloud of atoms with lasers from all 6 directions, left, right, up, down, forward, backward, you can create an optical molasses that slows the atoms no matter which way they're moving. With this technique, Physicists at institutions like the National Institute of Standards and Technology, NIST, can cool clouds of atoms to about 100 microkelvin. That's just 1/10,000th of a degree above absolute zero. It's a stunningly elegant way to use one of the fundamental properties of the universe, light, to tame the chaotic motion of matter. But why go to all this trouble? What do we gain from creating the coldest spots in the known universe? The answer is that it opens up a new world of technology and understanding. Perhaps the most well-known application is in the hospital MRI machine. MRI relies on superconductivity, a remarkable phenomenon discovered in 1911 by Heikki Kammerling Onnes. He found that when you cool certain materials, like a solid mercury wire, to a few degrees above absolute zero, their electrical resistance completely vanishes. This means that an electrical current can flow through a superconducting loop forever without losing any energy. MRI machines use superconducting magnets to generate incredibly powerful and stable magnetic fields. These magnets need to be bathed in liquid helium to keep them cold enough to maintain their superconducting state. Without our understanding of ultra-cold physics and superconductivity, this non-invasive window into the human body simply wouldn't exist. The same principle is now being explored for revolutionary applications like more efficient electric propulsion systems for aircraft, where superconducting motors and distribution systems could be 2 to 3 times lighter than conventional systems, a game-changer for future travel. Then there's the field of quantum computing, which you mentioned. The fundamental building blocks of a quantum computer are called qubits. Unlike ordinary computer bits, which are either a 0 or a 1, qubits can be in a state of superposition, both 0 and 1 at the same time. This is what gives quantum computers their potential for immense power. But this quantum state is incredibly fragile. It's like a perfectly balanced pencil on its tip. The slightest vibration or jostle from thermal energy will cause it to collapse, a process called decoherence. This is why quantum processors must be kept in those dilution refrigerators at temperatures often below 0.1 Kelvin. At these temperatures, the random thermal jiggling of atoms is reduced to a minimum, allowing the qubits to maintain their delicate quantum states long enough to perform calculations. Companies like IBM, Google, and others are in a race to build larger and more stable quantum computers, and a huge part of that challenge is the cryogenic engineering required to keep them cold. The pursuit of cold has also given us the most precise timekeepers imaginable, atomic clocks. These clocks work by measuring the vibration of atoms, much like a grandfather clock uses the swing of a pendulum. But if the atoms are hot and moving quickly, their vibrations get smeared out by the Doppler effect, making the measurement less precise. By laser cooling atoms to near absolute zero, scientists can hold them almost perfectly still, allowing them to measure the atom's natural vibration frequency with astonishing accuracy. The latest atomic clocks are so precise they wouldn't gain or lose a second in billions of years. This incredible precision is the backbone of the Global Positioning System, GPS. The timing signals from these satellites are what allow your phone to pinpoint your location on Earth. They are also essential for synchronizing our telecommunications networks and for conducting fundamental experiments to test whether the constants of nature are truly constant. And now for one of the most mind-bending concepts to emerge from this field, negative absolute temperature. It sounds like a contradiction, doesn't it? How can something be colder than the coldest possible temperature? The secret is that negative Kelvin doesn't mean colder than absolute zero. Instead, it describes a system that is, in a way, hotter than any positive temperature. In a normal system at a positive temperature, most atoms are in low-energy states, and only a few are in high-energy states. As you add heat, you push more atoms into these high-energy states. At a negative temperature, this situation is inverted. More atoms are in high-energy states than in low-energy states. It's a bit like having a population pyramid of a city that has more elderly people than children. It's an inverted, unnatural state. This can only happen in special systems where there is a limit to how much energy the particles can have. When physicists at the Ludwig Maximilians University Munich and the Max Planck Institute created such a system in 2013, they weren't creating something colder than cold. They were creating a system so energetic that heat would actually flow from it into any other system. regardless of whether that other system was at +1 Kelvin or +1000 Kelvin. These strange systems can even be used to create heat engines with efficiencies that appear to be greater than 100%, though without violating the conservation of energy, showing us that the physics of temperature still has profound surprises in store for us. This journey into the cold has done more than just give us new gadgets. It has given us a new lens through which to view the cosmos itself. By creating exotic states of matter like Bose-Einstein condensates, where thousands of atoms lose their individual identities and merge into a single quantum wave, scientists can simulate conditions that are otherwise impossible to study. They can use these ultra-cold atoms in grids of light called optical lattices to act as stand-ins for electrons in a complex material. This allows them to model and understand the bizarre behavior of superconductors or other exotic materials. Some researchers even see parallels between the strange properties of these lab-made quantum fluids and the greatest mysteries of the universe, such as dark energy, the mysterious force causing the cosmos to expand at an accelerating rate. By studying the weird physics that happens in the quiet and cold of their laboratories, they are, in a small way, probing the secrets of the birth and fate of the universe itself. So, from the hospital room to the quantum computer lab, from the satellite orbiting Earth to the fundamental theories of cosmology, the pursuit of the ultimate cold has woven itself into the fabric of our modern world. It's a powerful reminder that the most abstract scientific quest, the simple desire to see how far a boundary can be pushed, often yields the most practical and transformative fruits. And as we continue to coax matter closer and closer to that final unattainable zero, we can be sure that the universe has more wonders and more revolutions waiting for us, just a fraction of a degree away. As we approach the conclusion of our journey into the realm of absolute zero, we need to confront the most perplexing and fascinating aspect of this ultimate cold, its deeply quantum nature. The classical picture of atoms simply slowing down until they stop completely fails utterly to capture what really happens near absolute zero. Instead, we enter a domain where the bizarre rules of quantum mechanics dominate, where particles behave as waves, where certainty gives way to probability, and where the very concept of nothing takes on new meaning. Let's return to that seemingly simple question: what happens to atoms at absolute zero? If we were to rely on the classical intuitive physics of Newton, the kind that governs swinging pendulums and flying baseballs, the answer would be straightforward. At absolute zero, all motion would cease. Every atom, every molecule would come to a dead, complete, and utter stop. It would be a perfect crystalline and frozen stillness. Imagine a crowded dance floor where the music represents heat energy. As the music slows, the dancers move more and more slowly. When the music stops completely, according to classical thinking, every single dancer would freeze in place, mid-step, perfectly motionless. This seems logical, right? It's the ultimate chill. But our universe, especially when we probe its deepest secrets, is rarely so simple or so obedient to our everyday intuition. The reality is far more interesting, and it forces us to abandon our classical thinking for the bizarre and counterintuitive rules of the quantum world. The reason the classical picture fails is because of one of the most fundamental and mind-bending principles in all of physics: the Heisenberg uncertainty principle, formulated by Werner Heisenberg in 1927. This isn't just a minor technicality. It's a cornerstone of how our universe operates at the smallest scales. The principle states a fundamental limit to what we can know about a particle. Specifically, we cannot simultaneously know both the exact position and the exact momentum of a particle like an electron or an atom. The more precisely you pin down its location, the less you can know about where it's going and how fast, and vice versa. It's not a limitation of our microscopes or our technology, it's a built-in feature of reality itself. Now, let's apply this to our idea of absolute zero. If an atom were to truly come to a complete and absolute stop, what would we know about it? We would know its momentum with perfect precision. It would be zero. We would also, in that frozen state, know its exact position. It would be sitting right there, perfectly still. But this is precisely what the uncertainty principle forbids. It's like a cosmic rule that says, Thou shalt not be completely still and perfectly located at the same time. The universe seems to demand a little bit of fuzziness, a little inherent jitter, at the most fundamental level. Therefore, even if we could remove every single bit of heat energy, reaching the fabled absolute zero, the atoms would not stop moving. They are compelled by the laws of quantum mechanics to retain a residual, irreducible minimum of motion. This is what physicists call zero-point energy. It's the energy an atom possesses simply by virtue of existing in a quantum universe, the energy it has even when it's in its absolute lowest possible energy state. Think of it as the universe's default baseline hum of activity. This isn't just a wild theoretical idea. It has very real, measurable consequences that we can observe in a laboratory. The most beautiful and dramatic example of this is the behavior of helium. Think about any other substance, water, nitrogen, oxygen, iron. When you cool them down sufficiently, they freeze into solids. They form orderly, rigid crystal lattices where the atoms are locked into place. But helium is a rebel. Under normal atmospheric pressure, helium simply refuses to freeze. Even if you cool it down to within 1,000th of a degree of absolute zero, it remains a liquid. You can have a bucket of liquid helium at 1 Kelvin, at 0.1 Kelvin, at 0.001 Kelvin, and it will still slosh around. It won't become solid. Why? Because the zero-point motion of helium atoms is so incredibly vigorous that it prevents them from settling down into the fixed positions of a solid crystal. Helium atoms are exceptionally light and the forces between them are very weak. This lightness means that the quantum jitter is a much bigger effect for them than for heavier atoms. It's like trying to get a hyperactive toddler to sit perfectly still in a single chair. The inherent energy is just too great. The only way to force helium to solidify is to apply immense pressure, literally squeezing the atoms so close together that their interactions overcome the zero-point motion and force them into a crystalline structure. This stubborn liquidity of helium is a direct, visible, and spectacular proof that the quantum world is real and that zero-point energy is not just a mathematical abstraction. Now let's zoom in even further, from the atoms themselves to the electrons that swarm around them. At room temperature, we can often get away with thinking of electrons as tiny, classical charged particles zipping around. But as we approach absolute zero, their true quantum nature is unmasked. Here we run into another fundamental quantum rule, the Pauli exclusion principle. This principle, discovered by Wolfgang Pauli, states that no two identical fermions, a category of particles that includes electrons, protons, and neutrons, can occupy the same quantum state. It's like a cosmic no double booking rule for particles. Imagine a multi-story car park where each parking space represents a specific energy level. In a classical world, as you cool the system down, all the cars, electrons, would just roll down to the lowest, cheapest level of the car park. But the Pauli exclusion principle changes everything. It says that only one car can park in each space. So as you cool the system, the electrons fill up the car park from the bottom level upward. At absolute zero, the car park is perfectly filled up to a certain level, but all the levels above that are completely empty. The highest energy level that still contains electrons is called the Fermi energy. Here's the amazing part. For the electrons in a piece of metal, this Fermi energy is enormous. It corresponds to a temperature of tens of thousands of kelvins. This means that even at absolute zero, the electrons in a metal are not slow and sluggish. A vast number of them are still zipping around at tremendous speeds, thousands of kilometers per second, because they are forbidden by the Pauli principle from all crowding into the lowest energy state. This quantum behavior solved a mystery that baffled 19th century physicists. They couldn't understand why the electrons in a metal, which they knew were there, didn't seem to contribute much to the metal's heat capacity, its ability to absorb heat. According to classical physics, each electron should have been soaking up thermal energy and contributing to the heat capacity. But they didn't. The answer, provided by quantum mechanics, was that most of the electrons were already locked into their high-energy states by the Pauli exclusion principle and couldn't easily be bumped into a slightly different state by a little bit of heat. Only the electrons near the very top of the filled levels, right at the Fermi energy, had available spaces to move into, and could participate in absorbing heat. This quantum understanding, described by the Fermi-Dirac distribution, was a monumental triumph. Perhaps the most dramatic and beautiful demonstration of quantum mechanics at low temperatures is the phenomenon of Bose-Einstein condensation, BC. While electrons are fermions and obey the Pauli exclusion principle, there is another class of particles called bosons, named after Satyendra Nath Bose, that do not. Bosons are the social butterflies of the particle world. They have no problem all crowding into the exact same quantum state. In the 1920s, Satyendra Nath Bose and Albert Einstein predicted that if you cool a gas of certain bosonic atoms to a sufficiently low temperature, a miraculous transformation would occur. A macroscopic fraction of the atoms, millions or billions of them, would suddenly all collapse into the very lowest possible energy state. They would lose their individual identities entirely and merge into a single giant quantum entity. It would be like if all the dancers on that crowded dance floor, instead of just slowing down, suddenly began moving in perfect, synchronized unison, as if they were one single super dancer. This isn't just a theory anymore. In 1995, this state of matter was created for the first time in a lab, earning Eric Cornell, Carl Wieman, and Wolfgang Ketterl the Nobel Prize. In a Bose-Einstein condensate, the atoms are no longer separate little balls. Their wave-like nature, which is usually hidden, becomes dominant on a macroscopic scale. The individual atomic wave functions overlap and combine to form one single wave function that describes the entire condensate. If you take two separate BECs and let them expand into each other, you don't get a simple mixing of gases. Instead, you get an interference pattern, dark and bright bands, exactly like the pattern you see when you shine two lasers through a double slit. But this is a pattern made of matter, not light. It's a stunning visual proof that these atoms are behaving as waves and that they are all part of one coherent quantum object. The study of this ultra-cold quantum world has led to some of the most profound modern insights, blurring the lines between different fields of science. For instance, researchers at TU Wien and elsewhere have been exploring the deep connection between thermodynamics and quantum information theory. They've found that the act of cooling a quantum system to absolute zero is mathematically equivalent to the act of perfectly erasing the quantum information it contains. This is a breathtaking connection. It suggests that the reason we can never quite reach absolute zero, the third law of thermodynamics in action, is fundamentally linked to the limitations on how we can manipulate quantum information. In a theoretical, idealized world, if you had infinite control over a quantum system, an obvious impossibility, you might be able to reach absolute zero with finite time and energy. But in our messy, real world, the unattainability of absolute zero and the fundamental limits of information processing are two sides of the same coin. This brings us to the cutting edge, where new, seemingly impossible states of matter are being created. One of the most exciting is the supersolid. Imagine a material that has the rigid, repeating structure of a crystal, a solid, but whose atoms can flow through it without any friction whatsoever, like a superfluid. It's a material that is both ordered and frictionless at the same time, a paradox made real. This isn't science fiction. Researchers have begun to create such states in labs using ultra-cold quantum gases. This is only possible because of the weird, wave-like behavior of matter that dominates at these temperatures, allowing atoms to delocalize and form a rigid structure while simultaneously flowing freely. So you see, the journey toward absolute zero is not a journey into a dead static silence. It is a journey into the heart of quantum reality. As we peel away the distracting, masking layer of thermal noise, we don't find stillness. Instead, we find a world buzzing with zero-point energy, governed by exclusion principles and social bosons, a world where information and temperature are intertwined and where matter reveals its true, wave-like and collective nature. Absolute zero, far from being the end of the story, is the gateway to the strangest and most wonderful physics we have ever discovered. As we bring our exploration of absolute zero to a close, it's worth stepping back to appreciate the remarkable journey we've taken, from the earliest philosophical speculations about an ultimate cold to the cutting-edge quantum refrigerators of today, from the familiar experience of temperature in our daily lives to the bizarre quantum phenomena that emerge near absolute zero. This journey has revealed not just the properties of matter at extreme cold, but something fundamental about our universe and our place in it. Absolute zero, this seemingly simple concept of a temperature bottom, has proven to be one of the most fruitful ideas in the history of physics. What began as an extrapolation on a graph, the point where ideal gases would reach zero volume, has blossomed into an entire field of science that continues to yield surprises and insights. The pursuit of absolute zero has led us to discover entirely new states of matter, to develop technologies that have transformed medicine and communication, and to deepen our understanding of the quantum world that underlies reality itself. Perhaps the most profound lesson from our exploration is that the universe is far stranger and more wonderful than our everyday experience might suggest. Who could have imagined that by pushing temperature to its ultimate low, we would discover fluids that flow uphill without friction, electrical currents that flow forever without resistance, or gases that behave as single quantum waves? These phenomena aren't mere curiosities. They reveal fundamental truths about how nature operates at its most basic level. They remind us that reality, when examined closely, is far richer than our intuitions might suggest. The unattainability of absolute zero, rather than being a limitation, has proven to be an engine of discovery. Each new technique to approach closer to this ultimate cold has revealed new phenomena and posed new questions. Laser cooling, evaporative cooling, adiabatic demagnetization, each technological advance has opened new windows into the quantum world. The fact that we cannot reach absolute zero isn't a failure. It's an invitation to endless exploration, a frontier that recedes as we approach it, always offering new mysteries to solve. Our journey has also revealed the deeply interconnected nature of physical law. The third law of thermodynamics, which governs the unattainability of absolute zero, turns out to be intimately connected to quantum information theory. The behavior of ultra-cold atoms has implications for cosmology and the nature of dark energy. Superconductivity discovered in the ultra-cold laboratory now enables technologies that shape our modern world. In physics, as in ecology, everything is connected, and pushing at one frontier often reveals insights about seemingly unrelated domains. As we look to the future, the pursuit of ever colder temperatures continues. Researchers are developing new cooling techniques, exploring new quantum phenomena, and finding new applications for ultra-cold matter. Quantum computers, operating at temperatures within a few thousandths of a degree of absolute zero, may one day solve problems that are currently intractable. Quantum sensors, leveraging the strange properties of ultra-cold matter, may detect gravitational waves or dark matter. The horizon of the ultra-cold continues to expand, promising new discoveries and new technologies that we can barely imagine today. But beyond these practical applications, the study of absolute zero continues to fulfill a deeper human need, the need to understand our universe, to push against boundaries, and to wonder at the marvels of nature. In our quest to reach the ultimate cold, we're following in the footsteps of all those who have looked at the world with wonder and asked what if, and why not. We're engaging in one of the most fundamentally human activities, the pursuit of knowledge for its own sake, the drive to understand the world not because it is useful, though it often is, but because it is fascinating. So the next time you feel a chill in the air, or sip a cold drink on a hot day, or marvel at the image from an MRI machine, remember the incredible story of absolute zero. Remember that behind these everyday experiences lies a century-spanning quest to understand the nature of cold, a quest that has revealed a quantum world of astonishing beauty and complexity. And remember that this quest continues in laboratories around the world as we continue to approach but never quite reach the ultimate cold of absolute zero. In the grand tapestry of physical law, absolute zero stands as a fundamental limit, a reminder that nature places boundaries on what is possible, but that within those boundaries lies infinite variety and wonder. It is a destination we can never reach, but whose pursuit has transformed our understanding of the universe and our place within it. And for that, this ultimate cold has proven to be one of the most generative and inspiring ideas in all of science. A frontier that continues to beckon, to challenge, and to reveal the profound beauty of our physical world. Good night. and have a deep, calm sleep.